Okay, everyone, so we're going to get started. So last week we covered the majority of chapter 4. We covered precipitation reactions and we covered acid-base titrations as well as started redox. So tonight we're going to start off just by going over the challenge problems from Wednesday, which have to do with oxidation numbers and mostly with titration problems and acid-base problems. And then tonight, really the only new material we're going to go over is how to actually balance these redox reactions that we started to talk about on Wednesday. Okay, and so this is leading up to your exam this Friday, which is a long answer exam. It's on chapters 3 and 4. So tonight we're kind of finishing the last of the big material in chapter 4, and then Wednesday's SI will kind of be used to review the main points of chapters 3 and 4, as well as hit any topics that we haven't touched upon yet, if there are any, and yeah, make more problems to help you practice for your exam. In terms of main material, we're going over the last of it tonight. Okay, so the first one is an acid-base problem, a titration problem where you are reacting strontium hydroxide with hydrobromic acid, and you're basically asked what mass of strontium hydroxide needs to react completely with, and they give you a bunch of information about a bromic acid solution. And so I believe the answer to this may have been A. Yeah, it was A, 9.37, I think A was 9.39, depending on how you rounded it. I rounded it a bit different here. Your answer should have been A, though. And so ones like this, where they're giving you a lot of different numbers, they give you density, they give you a mass percent. This is also a titration problem, or kind of a react completely problem, right? We're going to associate that with acid base. So there's just a lot of information. And so one way I tried to kind of focus in on what I needed to do is I kind of did my unit analysis at the top, right? And so in a titration problem, which this again is kind of a derivative of a titration problem, you're always going to start with, or pretty much always start with the volume of solution that you're given the most information about, or all the information about. And so we're eventually asked about strontium hydroxide, which kind of tells us that we're going to need to start by focusing on hydrobromic acid, or HBr here. And so we're given how many, our volume, or how many milliliters of that HBr solution we have. And we were given a density, right? And so from milliliters of that solution, we can use the density to convert to grams of that solution, right? And then we're told that solution is about 84% HBr by mass. So once we have grams of solution, we can use the percent mass to solve for just pure grams of HBr, right? And whenever we convert between reactants and products, or just different species, we're always going to convert to moles. So I know we should convert from grams of HBr to moles of HBr, right? And now we're talking about acid base, which means we care about how much H plus and OH minus we have. And so I'm going to use that to help me transition from acid calculations to base calculations. Okay, so after kind of talking about the units, let's look at the actual numbers, right? So we were told that we have 12 milliliters of our solution, and that the solution is 1.239 grams per milliliter. Okay, so that's how many grams of solution we have. But we don't care about our solution, we care about HBr. So if the solution is 84% HBr by mass, that means in 100 grams of solution, we have 84 grams of HBr, right? So that's how I got that next conversion factor. Now that we have grams of HBr, I want to convert to moles. So 1 mole of HBr is a little bit over 80 grams, right? And then we convert from 1 mole of HBr contains 1 mole of H plus. So that top dimensional analysis, I just ran out of room, so I kind of calculated it out, came out and told us that we have 0.154 moles of just H plus, right? Protons, okay? And so from here, we're gonna kind of take the second half of these calculations, right? So if we know we have 0.154 moles of H plus, right? We know next that for every mole of H plus, we're going to have 1 mole of OH minus. Now, if you're asking yourself, where does this conversion factor come from? How do I know this? Whenever you're doing an acid-base problem and they're asking you, they're saying titrated, react completely, you reached endpoint, neutralization, all those terms are just telling you that somewhere in your calculations, you need to have 1 mole H plus to 1 mole of OH minus, because this only occurs at that titration point, equivalence point, neutralization point, right? So it said in this problem, it reacts completely, which infers this conversion factor. Okay, so that's where it came from. Now that we know how many moles of hydroxide we have, we're going to convert from moles of hydroxide to moles of strontium hydroxide, right? So it's 2 moles of hydroxide are needed to make 1 mole of strontium hydroxide. And then we just multiply it by the molar mass of strontium hydroxide to find that it would take 9.37 grams of the strontium hydroxide to react completely with the HBr. Okay, are there any questions on that problem? Okay.
Did you need to balance the equation in order to solve this, or did you just need the information given?
So if you look at the, I'll go back, and that's a pretty good point. The dimensional analysis kind of balances it for you. Like the math is correct if you do the dimensional analysis this way. And so, no, you don't really need to balance it. If you were to make like an ionic or an equation for this, it's a strong base reacting with a strong acid. And so your net ionic is just going to be H plus OH minus go to water. And pretty much all of your titrations, like this problem, a very classic titration problem, you're going to deal with strong acids and strong bases, in which the net ionic will always be H plus OH minus goes to water. And so if you get this dimensional analysis you know how to do it, you don't actually have to physically write out a balanced equation to get the right answer.
Okay, thank you.
Yep. And again, that's because conversion factors along the way kind of mathematically balance it for you, right? So in this dimensional analysis, we say 1 mole of HBr is 1 mole of H plus. Then later say 1 mole H plus is 1 mole hydroxide. And then we later say 2 moles of hydroxide is 1 mole of strontium hydroxide. Those 3 conversion factors combined are kind of like utilizing your coefficients in your balanced equation. Okay, any remaining questions on this one? Okay. So the next 2 are, again, pretty similar or relatively similar titration problems. So this one, it's perchloric acid, reacts with 9.24 milliliters of 0.0439 molar calcium hydroxide to bring it to endpoint. So again, endpoint here is really saying, note that your moles of H plus have to be equal to your moles of OH minus. And again, note here that you're using calcium hydroxide, a strong base, and perchloric acid, a strong acid. So again, a titration problem where we're using both strong acids and bases, which is very classic. So again, this is, in my opinion, the classic titration problem. And so notice in the question, they gave us both the volume and molarity of calcium hydroxide, which indicates to me that that's what we should start with, right? So they tell us that we have 9.24 milliliters of that solution. And so I'm going to convert that to liters. So 1 liter is 1,000 milliliters. Now that we have liters of that solution, I can use the molarity to convert to moles, right? So a 0.0439 molar solution just means that it is 0.0439 moles of calcium hydroxide per 1 liter of that solution. Okay, now that we have moles of calcium hydroxide, we're going to convert to just moles of hydroxide, right? So within 1 mole of calcium hydroxide, we actually have 2 moles of hydroxide. And then again, here is our key conversion factor. It said endpoint, so we know that we have 1 mole of hydroxide per 1 mole of H plus. That is a conversion factor you should always see in your dimensional analysis for these problems in 1127. And then we're going to convert from moles of H plus to moles of our entire acid, which is perchloric acid, HClO4. Okay, when we do all of this dimensional analysis out, it gets us that number in the numerator, right? So if you do that out, it comes to 0.00081127 moles of perchloric acid. Now, they told us that we have 60 milliliters of perchloric acid solution, which 60 milliliters is equal to 0.06 liters. And so to find the molarity of the solution, we take moles of HClO4, which is the 0.00811 number, and we divide it by its volume, 0.06 liters. Okay, and that gets us our molarity. When you actually put it into the calculator, it comes out to 0.0135, I believe, but rounding brought it to 0.014, which was, I think, option B, maybe option C, but whatever corresponds to that molarity. Does anybody have any questions? Okay. This one, again, is a very classic titration problem. But again, ones like this have appeared. I believe this was a multiple choice question on my exam, just with slightly different numbers. But here, you're told that you have a 1.2 gram sample of triprotic acid, and you use that to titrate or to react with 78.23 milliliters of 0.2187 molar potassium hydroxide, and they neutralize completely. Okay, so the neutralized or completely neutralized component here tells us, again, 1 mole of H plus equals 1 mole of hydroxide. Then it says, what is the molar mass of the acid? Okay, so to find a molar mass of the acid, we need two components, right? We need the grams of acid, which we have, right? We're told we have 1.2 grams of acid, and so we need moles of acid. Okay, so when we're going through our dimensional analysis, our goal is going to be to take information from potassium hydroxide and to convert it to find how many moles of this triprotic acid do we have. And remember that triprotic or a triprotic acid means it's an acid with 3 protons. Okay, so an example of a triprotic acid would be phosphoric acid. Okay, it just means 3 protons. Okay, so again, we're given both the volume and molarity of KOH, and so we're going to start with that. Okay, and so typically you start with the volume. So if we have 78.23 milliliters of KOH, I'm going to convert this to just liters, right? So 1 liter is 1,000 milliliters. And from converting it to liters, we can use our molarity to convert to moles, right? So a 0.2187 molar solution just means 0.2187 moles of potassium hydroxide per 1 liter of that solution. Now that we have moles of potassium hydroxide, we convert to just moles of hydroxide, so they're in a 1-to-1 ratio. And now that we have it in terms of moles of hydroxide, we can use our go-to conversion factor. So 1 mole of hydroxide is 1 mole of H plus, right? We're doing that because it says they completely neutralize each other, right? And then it's a triprotic acid, which means it takes 3 moles of H plus to make a single mole of H3A. This is just a shorthand version to tell me this is an unknown triprotic acid, right? And so the H3 just tells us 3 protons, and H3A is just 1 kind of molecule or mole of acid. And so when we do this calculation out, we find that we have 0.0057 moles of our acid, okay? And the question asked us, what is the molar mass of this acid? And so to find the molar mass, we take grams, right? So they told us that it weighed 1.203 grams, and we divide it by how many moles it was. So what we calculated was the moles. So it's 1.2 divided by 0.0057, and that tells us that every mole of this compound weighs 210.9 grams. Okay, so I believe that was answer D. Any questions on this one? Okay. So last time we kind of looked a little bit at redox. So this was just kind of a multiple choice redox question. What is the oxidation number of sulfur and SO32 minus. And so the answer to that, oh, sorry that it's a little bit blurry, is that it's positive 4. Okay, so remember that whenever we're looking at a molecule with a charge, right, SO3 has a charge of 2 minus, that means that the oxidation numbers, when we add them all up, will equal that charge, right? So when we add up the oxidation number of sulfur plus the oxidation number of oxygen times 3, because there's 3 oxygens in the molecule, they're going to add up to -2, because that's the charge, again, on the ion. And so oxygen, kind of looking at the rules, and if you're unfamiliar with the rules, we're going to go back over them tonight, but oxygen almost always has an oxidation number of -2. So 3 times -2 means oxygen contributes -6 to the oxidation number, and that means that sulfur needs to have a positive 4 oxidation number in order for the ion to have a charge of -2. Okay, so the answer to that should have been positive 4. Okay, a similar question, just fill in the blank. It's saying as perchloric acid is converted to, what is that, chlorite, chlorine has a blank of blank electrons. So you're going to have to say, did it gain or lose electrons, and how many? Okay, so this is really saying, what was your oxidation number before and after, and how much did it change by? And so when we look at HClO4, right, that is a neutral molecule, meaning the sum of the oxidation numbers needs to add up to 0. And so hydrogen almost always has an oxidation number of +1. Oxygen almost always has an oxidation number of -2. And so when we go through this math, we can find that chlorine should have had an oxidation number of +7 when it was perchloric acid, HClO4. In ClO2 minus, a chlorite ion, right? Chlorine plus 2 times the oxidation number of oxygen had to equal the charge, which was -1. And so because we know oxygen is almost always -2, for that to be true, chlorine would have had to be, or had to had an oxidation number of +3. And so when we're looking at this reaction, chlorine goes from a oxidation state of +7 to +3, which means it gained 4 electrons, right? That number changed by 4, and it's gain electrons, because remember, electrons have a negative charge, and chlorine's oxidation number is becoming more negative. So sometimes people kind of miss that and say, oh, the number's going down, so it lost 4 electrons. No, remember, if the number is going down, that means it actually gained that many electrons. Okay, so the answer to this would have been gain 4 electrons. Okay, number 6 was just kind of some oxidation number practice, because you're going to have to do lots of it in the redox section. And so I kind of label it at the top and then break it down after, right? So CO2 is a neutral molecule, again, meaning the sum of the oxidation numbers will add up to 0. There's 2 oxygens, each with a -2 charge. And so oxygen, again, had a charge of -2, or an oxidation number of -2. And carbon, when you solve for it, would have been +4, right? So I think I maybe asked for list all the elements, which is just why I reiterated that oxygen is -2. Now, sodium permanganate, right? That's actually an ionic compound. So that actually splits into different ions. So it splits into Na+, which is a monatomic ion, which means that the element has an oxidation number equal to its charge, right? So sodium plus, that tells us sodium has a +1 oxidation number. Okay, but changing our attention to permanganate, MnO4 minus, right? The sum of the oxidation number has to equal -1 because of the charge on permanganate. And if oxygen, there's 4 of them, each with a -2 oxidation number, that means manganese has to have a +7 oxidation number. Okay, so sodium should be +1, manganese +7, and oxygen -2. Any questions on either one of those before moving on to the remaining 3? Okay. So the third one was just kind of a quick test of knowledge. So carbon solid. So carbon solid and not in a diatomic state is the natural state of carbon. Handwritten notes, email your professors. Yeah, in terms of like what you can have and not, I'd assume it's the same as the first long answer, but definitely reach out to Dr. Katie or one of the respective professors. Okay, so again, carbon solid, that's its naturally occurring state. And whenever an element is in its naturally occurring state, its oxidation number is automatically 0. Okay, so carbon solid was 0. Now we actually kind of broke this down in the multiple choice one. This is perchloric acid, right? HClO4. So oxygen, again, is almost always -2. Hydrogen, almost always +1. And because that is a neutral compound, right, when we add them all up, it has to equal to 0. And for this to be a true statement, the oxidation number on chlorine would have to be +7. Okay. And then lastly, dihydrogen phosphate, or H2PO4 minus. The same thing applies to this one. When we add up all the oxidation numbers, they have to add up to the charge on the ion, which is -1. And so we have 4 oxygens, each with an oxidation number of -2. Okay, we have 2 hydrogens, each with an oxidation number of +1. And so when we kind of solve for what the oxidation number of phosphorus must be, it comes out to +5, right? And again, all of those oxidation numbers together have to equal -1. Are there any questions on oxidation numbers and states? There are. We'll be going over them again very briefly shortly, and then there'll be again another opportunity for questions as well. So this long answer question was again kind of more of a classic titration question. And so here we have a triprotic acid that is titrated or used to neutralize strontium hydroxide. And so again, what's the molarity of the acidic solution? Okay, so we're given more information about strontium hydroxide, so we'll start with that. So again, we have 185 milliliters. Okay, we're going to convert that to liters, so 1 liter is 1,000 milliliters, and we're going to use the molarity to convert from liters of solution to moles of strontium hydroxide. So a 0.25 molar solution means 0.25 moles of strontium hydroxide per 1 liter of solution. So we put that into the equation. And then again, we don't actually care about the strontium hydroxide, we only care about hydroxide. So 1 mole of strontium hydroxide is 2 moles of just our hydroxide, right? And then here again is our classic conversion factor that we'll always see, that in this course, 1 mole of hydroxide is 1 mole of H+, right? Acid base right here. And this is actually derived from the net ionic, right? H plus OH minus, a 1-to-1 ratio, goes to water. So this is actually kind of your balanced equation just right here. Okay, and then we're told this is a triprotic acid. So again, it takes 3 moles of H plus to make 1 mole of our acid. And when we calculate this, this is how many moles of acid we have that reacts, right? 0.0308 moles. And they ask you what's the molarity. So to find the molarity, you take moles of acid, which we just solved for. We divide it by volume of acid, which they told you was 225 milliliters, which is 0.225 liters. And this tells you that your solution was 0.137 moles, molar of triprotic acid. Okay. And the last challenge problem review question is kind of a derivative of titration, right? So it's not kind of our classic acid and base titration that we see, but here titration or titrated is really saying just reacts completely, right? That's all it's really saying in this context, and they're giving you a balanced equation. Now, if this one was tough, I took it basically, I'm pretty sure the equation itself is from my exam. I just changed the numbers. This is a great problem. And so hopefully as long as you understand it, that's great. But this is something that they have given in the past, and kind of problems similar could show up. Okay. And so here, excuse me, let me go back and just kind of read it. And so they say basically that you get manganese from ore, right? You get manganese 2 plus ions from an ore. Okay, and they're asking you what percent of this ore is manganese 2 plus ions, right? And it's saying, kind of to help you solve this, that the manganese ions react completely with sulfate ions from aluminum sulfate. And they tell you that it takes 51 milliliters of 0.22 molar aluminum sulfate to titrate or react, right? They mean the same thing, with all the manganese ions from the sample. Okay, and so let's kind of look at the math here. So again, in this case, they said titrated, which kind of just means react completely. And whenever you're kind of dealing with one of these problems, always start with the species or the compound that they give you the most information about, okay? Or the one that they don't ask for at the end, right? They're asking about manganese at the end of this problem, and they give you both the molarity and volume of aluminum sulfate, okay? And so because we're solving for manganese at the end, that tells me let's start with aluminum sulfate and see where we can go. Okay, so we have 51, a little over 51 milliliters of aluminum sulfate solution. We're going to convert this to liters of solution, so 1 liter is 1,000 milliliters, and then we use the molarity to convert to moles, so 0.2285 moles of aluminum sulfate per 1 liter. Now, you might notice in the equation given that aluminum sulfate and magnesium ore were not in the equation. But what was in the equation as reactants were manganese 2 plus, which is the ions coming from the ore, and sulfate, SO4 2 minus. And so kind of a difficulty or a challenging part of this problem is realizing that when you see, and I'm going to go back a slide, when you see sulfate here in the equation given, that's the sulfate from aluminum sulfate. So that's telling you, okay, once you have moles of aluminum sulfate, let's convert to just moles of sulfate. Okay, so 1 mole of aluminum sulfate is, and we can tell from the subscript, 3 moles of just sulfate. Okay, and from our balanced equation, again, I'm going to go back one slide for a second. From our balanced equation, the ratio from sulfate, 1, to manganese 2 plus, which is the manganese that comes from the ore, right, is 1 to 8. Okay, and so that's how I know that per 1 mole of sulfate, we have 8 moles of manganese 2 plus. Okay, and then I just use the molar mass to solve for how many grams of just manganese do we have. And when I solve for it, it's down below. I got 15.44 grams of just our manganese. Okay, and they asked us, in like for the final question, is what was the mass percent of manganese in the ore? Okay, now we basically solved for stoichiometrically, like based on all of our numbers, we had 15.44 grams of pure manganese, and they told us that this was in a sample of 23 grams of ore. Okay, and so the mass percent of manganese in the ore is 15.44 divided by 23, and then you multiply it by 100 to turn it into a percent. Aluminum is not included in the equation, probably because it is a spectator ion, right? So it's very similar to in precipitation reactions. We don't really care about ions that don't become the precipitate because they really have nothing to do with the reaction, right? They're just floating around. They don't actually do anything. While in this, what they're saying is that hydrogen, right, when it combines with sulfate, right, these react with manganese to make manganese in the 3 plus state instead of 2 plus state. And again, we get water and sulfur, right? So all of these components are reacting in some way in this problem. If you included aluminum in this equation, it would just be in the same state on either side. It would be aqueous, wouldn't change, and therefore spectator ion, and you don't really care for it. Okay, I think them leaving it off is also them checking your knowledge, seeing if you can apply it. Okay, you don't see aluminum sulfate, but can you apply that based on the equation, you need to convert to moles of sulfate and go from there. It's just, yeah, it's not really a needed piece of information, as well
Um,
as a good check.
isn't that the wrong molar mass for uh manganese?
What's manganese?
54.94.
Uh, okay. Maybe. I don't know. On the table I thought I saw, maybe that was a 9. Anyways, I don't think it would, you might get 15.5.
It only changes it by like 0.1%, but
Yeah, they would overlook that. That's, yeah.
okay, thank you.
Yeah. Any other questions? Okay. So I'm going to kind of go through oxidation numbers pretty quickly. There is a section after kind of, I think I have 2 or 3 review slides that we're kind of going to stop. I'm going to have you guys sign in, and we're going to kind of go over any remaining questions of things we've gone through in chapter 4 that you guys have before going on to balancing redox. So just if you have any questions, save them. In about 2 minutes, we can go over any remaining questions. So just as a quick review of oxidation numbers, right? So this is kind of the overarching rules that we see, right? So we have kind of several different compounds we come across, right? We have monatomic ions, which just means it's an ion with a single element, right? And all our rule is for that is that the oxidation state is equal to the charge, right? So K plus, right, a potassium ion would have an oxidation state of +1 because its charge is +1. Okay, neutral compounds, so things like CO2, right, things without a charge. When you add up the oxidation numbers of all the elements, it should equal 0, right, because it's a neutral compound. And then kind of like our third rule is that whenever we're dealing with an ion or a charged compound, whenever we add up the oxidation states or oxidation numbers of all the elements, they'll equal that charge on the compound, right? We've seen all of that. But in terms of actually assigning oxidation numbers, here's kind of your rules to help you figure it out. And typically, you only really see like oxygen or hydrogen or known elements in your compounds. Like you know all the oxidation numbers except for one element. And that's typically the one that's oxidized or reduced. Not always, but probably 95% of the time. Okay, so just a reminder that elements in their natural states have an oxidation number of 0, right? So basically any metal as a solid, unless it specifically has a charge. Remember all your diatomic gases, so H2 gas, O2 gas, N2 gas, F2 gas, all that. All your diatomic gases, remember. Fluorine, if it's in a compound, will always have an oxidation number of -1. Oxygen has an oxidation number of -2. The exception that you do see, and that's probably one or a couple problems you've come up or like seen this problem, in peroxides, oxygen has an oxidation number of -1. So like H2O2, hydrogen peroxide, each oxygen has a charge of -1 or oxidation number. On an exam, that is probably not something that they'll bring up. They kind of really want to test, do you know how to assign oxidation numbers? Do you know how to balance redox? A peroxide's kind of like a weird exception that, again, keep it in the back of your mind, but it's not something you see often. And then hydrogen almost always has an oxidation number of +1. Again, there might be 1 or 2 exceptions, but you wouldn't be introduced to that on the class. On an exam. Okay. Diatomic gases are for things that are diatomic gases, the natural states. And so your oxidation number is 0, right? If you're in your classic standard state, your oxidation number is 0. Okay. And so that applies to any diatomic gas that is their standard state. Okay. Any questions remaining? So titrations, I didn't really go over it again tonight because we went over it Wednesday, redox terminology, which we'll kind of use through, we have 2 practice problems. or oxidation numbers. Any questions on any of those topics? Okay, if there are no questions, we will begin. Again, I have 2 redox problems for us to go over. After this is kind of my how to balance a redox reaction rules. The first one we're going to break down pretty slowly. The second one we'll go through a little bit faster, but again, I'll be referencing these steps along the way the entire time, okay? So if any of these steps don't really make sense to you, maybe seeing me, having that step out with a real example will help you. One thing that, how I balance it, I always start by balancing redox reactions in acid, then I convert it to base if needed after. A lot of people ask, how do you know if it's in an acid or base reaction? On the exam, they would tell you, and if they don't specify, and I'll tell you one thing to look for, but if you don't see either one of those things, if they don't say anything, assume it's acid, right? If it's in base, they will definitely specify it's in base. If they say nothing and give no indication, they probably just want it in acid. Okay, so how do you balance a redox reaction? So your first step is to split your reaction into 2 half reactions. Okay, so typically there's going to be 2 elements that are what I'll kind of call atypical elements, right? They're not hydrogen, they're not oxygen, and you'll see them on both sides of the reaction, obviously. So a lot of times it's metals, sometimes it's halogens, but typically you split them into 2 half reactions, right? So if you have like chlorine and manganese, right? All your chlorine species, you're gonna write in 1 half reaction. Your other one will be your manganese components, okay? And your first step, and this is probably one I would star or underline because you don't often need to do this in problems, and so people forget on exams. But this first step, if you do not do it, your rest of your work will look right, but it will all be wrong, okay? So make sure, it's so important to make sure you balance all non-hydrogen and oxygen atoms, right? And so like the chlorines, for example, that's something that you would have to balance, or manganese, okay? And so one of my examples tonight requires us to do this. If you don't do it, again, unfortunately, the rest of it will not be correct. Okay, but on a long answer exam, they would give you some partial credit, but really make sure you do that. It only takes about 2 seconds. But again, people forget because you don't often need to in most problems. Okay, your next step is to balance oxygen by adding water. Okay, so you're going to add H2O to one of the sides to balance oxygen. Okay, after that, you're going to balance your hydrogen molecules by adding hydrogen ions, H+, also known as protons, to one of the sides of your equations, like on the reactant or product side, again, to balance. Then your last step to balance your each half reaction, right? These kind of sub-points are each just to balance 1 half reaction, right? The last step is to balance charge by adding electrons, okay? And after you do all those steps, you will have a balanced half reaction, and so you'll do the same exact steps for the other half reaction as well, okay? Your next step here, and kind of like a good self-check mechanism, after you've balanced your half reactions, you should notice electrons should be a reactant in 1 half reaction and a product in the other. If you see your electrons are both reactants or both products, that means you messed up somewhere while balancing one of your half reactions, and so go back and check, right? You should always see electrons on opposite sides of your equation when comparing your half reactions, okay? So once you check to make sure they're on opposite sides of the equation, your next step would be to multiply each half reaction by a coefficient so that you have the same number of electrons in each half reaction, right? If you want them both to transfer the same number of electrons. So if half reaction 1 transfers 2 electrons, half reaction 2 transfers 6, right? You'd want them both to transfer 6 electrons. So you'd multiply the first one, which transfers 2 electrons, by 3. Therefore, they both transfer 6 electrons, okay? One of your last steps is just to add all your reactants from both half reactions and all your products together, right? So just write your half reactions as one giant reaction. And then you're going to see often that you should have electrons on both sides, and you will most likely have water and H plus on both sides. If this is the case, you're just going to cancel them out, right? So if you have 2 water molecules on the reactant side and only 1 on the product, right, you cancel them out, and you would have remaining just a single molecule of water on the reactant side. Okay, and again, we'll get into an example, and I really broke it down, the first one kind of slowly to exemplify these steps. Okay, this set of steps you'll notice looks almost exactly the same. This is how to balance a redox reaction in base. The only difference is the step at the end. They're both in red, right? So you'll notice right before the red words, it says cancel out components found on both sides. That was our final step to balance in acid. And so once you've balanced your redox reaction in acid, okay, what you're gonna do is add an equal amount of hydroxide to each side to neutralize H plus. Okay, basically the hydroxide that you add to the H plus, right, they become neutral, well, they neutralize each other, right? They become water on that side. And then you might just have to cancel out water that appears on both sides. But at that point, you have a balanced redox reaction in base. And again, one of our examples will show that. I think adding the hydroxide in terms of like writing it as words sounds weird, but I think most people seem to think it makes a fair amount of sense once we actually go over an example problem. Okay, and so this first one, we're gonna balance it in acid and base. I'll actually kind of spoil the ending. It's actually the same in acid and base. It's a really kind of weird circumstance. I just kind of made up these, I mean, they're real compounds, but I just kind of randomly did it. And so in this weird case, balancing an acid and base are actually the same, and I'll show you why. But our next example will show better balancing in base. And so the first step that I did here is I actually went to assigning my oxidation numbers and writing out my terminology. Okay, and so any known oxidation number I wrote above, right? So you'll see in HNO3, I wrote +1 above H because hydrogen has a +1 oxidation number. And anytime you see oxygen, you'll see a -2 above it because oxygen almost always has an oxidation number of -2. And so based on these and the rules I went over, I was able to find my oxidation states, right? So iron in iron solid, that's its natural state, right? And so it has an oxidation number of 0. Nitrogen in nitric acid, based on my math, would have an oxidation number of +5. Iron in Fe2O3, that's actually an ionic compound, so you could break it up kind of differently. But really, either way, you would find that iron would have a +3 charge there. And then nitrogen and nitrogen monoxide would have an oxidation number of +2. Okay, right? So we see iron, which goes up in oxidation number, and nitrogen, which goes down in oxidation number, looking from reactant side to product side. So that's something that you'll see in all redox problems. Okay, and so based on these numbers, I kind of just assigned my terminology, right? So iron went from 0 to +3, right? And so it became greater in oxidation number, and so it got oxidized, right? And I kind of described next to it, lost 3 electrons. Remember, if you become more positive, that means you lost electrons. Okay, nitrogen went from an oxidation number of +5 to +2, meaning it was reduced, right? And if it was reduced, that means it actually gains electrons. How many? The difference between 5 and 2 is 3, so gained 3 electrons. Okay, what's the oxidizing agent? Remember, the oxidizing and reducing agents aren't elements, they are reactants. And so the oxidizing agent is the whole reactant that contains the element that's reduced. Okay, nitrogen is reduced. What reactant is nitrogen a part of? HNO3, right? Nitric acid would be your oxidizing agent. What's your reducing agent? Your reducing agent is the reactant that contains the element that's oxidized. So iron is oxidized. How does it appear as a reactant? It just appears as iron, Fe. And so your reducing agent is just Fe. Okay, so again, that's just kind of wasn't asked about, but going over the terminology, you'll definitely be asked that. And so definitely make sure you feel comfortable doing that. And so we split it into half reactions, right? I said kind of take your less common elements and split them up, right? So our less common elements here in terms of redox reactions, right? We don't see iron that much, so iron should be in one. Nitrogen change in oxidation number, so we're going to put that in the other. And so really what we're doing by splitting them into half reactions is splitting them into the oxidized half reaction and the reduced half reaction, right? That's really what we're doing. And so this is me just showing you what each of those is. Okay, you do not need to label them on an exam, the oxidized reduced ones, but from the previous slide, knowing what's oxidized and reduced, you would know that. Okay, so we're going to focus first on the iron one. And again, we're going to break this down pretty slow. So remember, this first equation is showing the first step, which remember is to balance any non-hydrogen or oxygen atoms. And again, this step is so essential. People forget it because most redox reactions that you balance, you don't need to do it. The step's already balanced. But in this case, we had only one iron on the reactant side, two on the product side. And to balance this, we just put a coefficient in front of iron solid, right? So 2 iron solid goes to iron 3 oxide. Okay, so now my irons are balanced. Once I have those balanced, my next step is to balance oxygen. And how do we balance oxygen? We add water. So we have no oxygen on the reactant side. We have 3 on the product side, indicating to me that we need to add 3 molecules of water onto the reactant side in order for oxygen to be balanced. Okay, so up to this point, we would have both iron and oxygen balanced. Okay, but now that we've added water onto the reactant side, we have hydrogen on the reactant side, and we have 0 hydrogen on the product side. And so we overcome this by adding hydrogen ions or protons to balance it, right? So if we have 3 molecules of water, right, each molecule of water has 2 hydrogens, that means the reactant side has a total of 6 hydrogens. And so we have to add 6 H plus ions onto the product side for those to be balanced. Okay, so we do that, and at that point, all of our elements, iron, oxygen, and hydrogen, all of them are balanced. The only thing that is not balanced is our charge. Okay, and that's kind of a unique thing about redox reactions. We actually have to balance the charge. So when we look at the reactant side, we have species that are all neutral, right? Water has no charge and iron has no charge. So when we look at the total charge on the reactant side, it would be equal to 0. When we look at the product side, however, we have iron 3 oxide, which has no charge, but we also have 6 H plus ions, meaning the product side has a charge of positive 6. So we have to add electrons on one side to balance the charges. And so what we have to remember is that electrons have a negative charge, and so we're going to add them to the side with a more positive charge, right? So the product side has a positive 6 charge, the reactant side 0 charge, and so for the charges to balance, we have to add 6 electrons onto the product side. So that's how I get the very bottom. That is my balanced half reaction for the iron half reaction, right? So 3 waters, 2 irons go to iron oxide, iron 3 oxide, plus 6 protons and 6 electrons. So our next step is to do the same thing, but for the nitrogen half reaction, right? So this is kind of showing all those steps just in one. And so our first step would be to balance any non-hydrogen and oxygen atoms. And so we'd look at nitrogen, there's 1 on each side, and so that's already balanced. So you don't have to do that every time, which is again why people sometimes forget. So there's 1 nitrogen on each side, so we move on to balancing oxygen. Right, so there's 3 oxygens on the reactant side, there's only 1 on the product side, and so to balance oxygen, we're going to add 2 molecules of water, again, to the product side. Because we just added water, however, we now have 4 protons or 4 hydrogens on the product side, but we only have a singular hydrogen on the reactant side. And so to balance hydrogen, we add 3 protons to the reactant side. At this point, again, hydrogen, nitrogen, and oxygen are all balanced in terms of how many are on each side, and our last step is just to balance charge. So the products in this half reaction are all neutral, meaning that our product side has 0 charge. When we look at our reactant side, nitric acid has no charge, but we have 3 protons, right? 3 times H plus. So a positive 3 charge exists on the reactant side. And so to get rid of this, we add 3 electrons to the reactant side. Therefore, our charges as well as our atoms are all balanced. Okay, and so all I did at the bottom there was rewrite my equation with all my components. 3 electrons plus 3 hydrogens plus nitric acid goes to nitrogen monoxide plus 2 molecules of water. Okay. Now what we'll notice is in the iron equation, right, we had 6 electrons on our product side, while in our nitrogen, right, the one that include nitrogen compounds, that half reaction had 3 electrons on the reactant side. Okay, so because the electrons are on opposite sides of the equations, that's a good sign. That means we probably balanced or mostly balanced this correctly. Okay, but what we need to do is make sure that the same number of electrons are present in both of the half reactions. And so because there's 6 electrons in the iron one and only 3 in the nitrogen one, I'm going to multiply the whole nitrogen half reaction, right, by 2, right? So I just kind of rewrote it below. That equation is now 6 electrons plus 6 protons plus 2 nitric acids go to 2 nitrogen monoxides plus 4 waters. My next step from here is just to write, combine both half reactions together and write all my reactants going to all my products, right? So I'm just writing all the reactants together, then all the products. Okay, and the final step from here is cancel out things that exist on both sides. Okay, so one thing that should always cancel are our electrons, okay, and those are circled, right? There's 6 electrons on each side. They cancel each other out and should not appear in your final equation that you write, right? Underlined, we have water, right? So we have 3 molecules of water on the reactant side, 4 on the product side, and those are going to cancel out. And in our final equation, we should just see a singular molecule of water on the product side, right? You're basically just subtracting 3 water molecules from either side. Now an arrow above it, we have 6 H plus on each side of the equation, right? So those will completely cancel each other out, and we will not, in this problem, have free H plus in our final equation. And so again, this slide is kind of just showing though that kind of rough equation where we're still canceling things out, and then below it is the final version, right? So your final equation here should have been 2 iron molecules plus 2 nitric acids goes to iron 3 oxide plus 2 nitrogen monoxides plus a singular molecule of water. Okay, and because there is no H plus in this equation at all, it's technically balanced in both acid and base. Okay. Our next example will show us how to balance in base. But this one, it was not on purpose. It actually just came out that you couldn't really balance it or do the typical steps to balance in base. Again, because there's no H plus in the final equation, because they just happen to cancel out, it's already balanced in both acid and base. Are there any questions on this balancing problem before moving on to the next one?
So because there's 6 hydrogens on both sides, you can just cancel them out? That's why?
Yep, you basically do the same thing with electrons in water. Basically what you're doing is subtracting it from both sides, right? So for water, we subtract 3 waters from both sides, leaving 0 waters left on the reactant side, which is why we don't see it, and just a singular water on the product side. Similarly, we subtract 6 H plus from the reactant and product side, leaving us with 0 of them on both sides.
Okay, thank you.
Yeah. Any remaining questions?
I get that we have to cancel out the electrons. Do we have to do the same thing for the hydrogens if for whatever, I guess they would equal each other anyways, but would we have to make sure they cancel out?
In this problem or in general?
In general.
In general, you will typically, again, this is one of the very few problems I've ever actually seen where H plus completely cancels each other out. Typically, it'll act very similar to water, where you will have more H plus on one side than the other, And so it partially cancels out, but not completely. And you'll see that in the next problem. The next problem will come out a little bit more typical comparatively. Again, this one was a little bit weird.
Okay, thank you.
Yeah. Any remaining questions? Okay, so another redox example. So here it is. I'll just show it kind of briefly. We'll kind of skip through the steps a little bit quicker, but I'll still try to highlight them. So on the first slide, again, I kind of just rewrote the equation. And again, it's good practice while you're practicing these before the exams to label things, because they will ask you what is oxidized, what's reduced, what are your oxidizing and reducing agents. So it's good to practice that. So I kind of did that. And so here, again, hydrogen and all these compounds would have an oxidation number of +1. Oxygen and all of these would be -2. And from that, I'm able to find the oxidation numbers of manganese on each side and sulfur. And what I find is that manganese goes from +7 to +2, meaning it was reduced, right? It went down 5 in terms of oxidation number, while sulfur went from +4 to +6, making it oxidized. Okay, and again, the oxidizing reducing agents are as, they're what they're labeled as. Again, remember that your agents, so your oxidizing reducing agents are reactants, right? Full reactants, while your what's oxidized and reduced are always only going to be just elements. Okay. Okay. And so here is how I balance. These are actually both half reactions that I balance. And so I start with the manganese. So manganese with 4 oxygens minus, I think that's permanganate, goes to manganese 2+. So we first check to see, is manganese balanced? There's 1 on each side, so we move on. We balance oxygen by adding 4 molecules of water to the product side, right? We have 4 oxygens now on both sides. From here, we balance hydrogen by adding H+, right? So there's 8 hydrogens on the product side because of the water we just added. And so we add 8 H+ to the reactant side. And now we balance the charges. Now, definitely be careful with the charges in a problem like this, right? So we look at the product side, it is a charge of +2. Okay, and we look at the reactant side, it has a +8 charge from the protons, but permanganate also has a -1 charge, which means the total charge on the reactant side is +7. Okay, and so to go from a charge of +7 to +2, we basically add 5 electrons to the reactant side to balance that charge. Okay, and so written kind of in parentheses below it is just me rewriting all the reactants going to all the products of the half reaction we just balanced. Now that we've balanced that half reaction, we turn our attention to the half reaction involving sulfur. Okay, so we first check, is sulfur balanced? Yes, there's 1 on both sides. So we move on to balancing oxygen, right? We have 3 oxygens on the reactant side, 4 on the product side. And so we add a singular molecule of water to the reactant side so that oxygen balances. Okay, the next step is to balance hydrogen. So we have a total of 4 on the reactant side now, 2 from H2SO3 and another 2 from water. And we only add a single 1 on the product side, meaning we have to add 3 H pluses to the product side for hydrogens to balance. Okay, when we look at the charges, the reactant side, all of the compounds are neutral, so there's 0 charge on the reactant side. When we look at the product side, we have a charge of +2, right? There's a +3 charge from the protons, but a -1 charge from HSO4 minus. And so a total of a +2 charge. And so we add 2 electrons to the product side for charge to balance. And again, in parentheses, I wrote just all my reactants going to all my products. My balanced half reaction. Before moving on, are there any questions on how to balance those 2 half reactions? So there's kind of a lot going on here, but let's just start at the top. So the things in parentheses are exactly what were on the last slide, right? So right here, so the thing that starts with 5E minus is our balanced half reaction for manganese, and the one below in parentheses that starts with a singular molecule of water, that is our sulfur-containing half reaction. Okay, so remember that when we're looking at our half reactions, our balanced half reactions, we should have electrons on opposite sides of the equation. So in the manganese half reaction, we have 5 electrons on the reactant side. Oh, I don't even know how that just came up. I didn't even touch my computer. That was weird. We have 5 electrons on the reactant side. And in our other half reaction, we have 2 electrons on the product side. So again, because they're on electrons on opposite sides of the equation, that indicates that we at least mostly balanced our half reactions correct. Okay, and what we need to do is multiply the equation or these half reactions by some coefficient that allows there to be equal number of electrons, right? And so in the first one, where we have 5 electrons, we're going to multiply that entire half reaction by 2. In the sulfur half reaction, which contains 2 electrons, we're going to multiply it by 5. This is so that there's 10 electrons transferred in both half reactions, allowing electrons to cancel. Okay, so all I did, was kind of multiply it out. So that whole top half reaction multiplied it by 2. The sulfur one I multiplied by 5. And then kind of at the bottom here, I just added all my reactants together with all my products. So my reactants were 10 electrons plus 16 H plus 2 permanganates plus 5 waters and 5 sulfurous acids, right? These are my reactants from my 2 half reactions combined, and these go to all the products of the 2 half reactions combined, okay? Whenever you combine your 2 half reactions, the things that will cancel will be your water, H plus, and electrons, right? Those are the things to watch for whether they cancel. Okay, and so what we see is that we have 10 electrons that are transferred or on both sides of the equation, and so these will cancel out completely. Okay, so you won't see it in the final equation. When we look at H plus, we have 16 on the reactant side, only 15 on the product side, and so what we basically do is subtract 15 H plus from both sides of the equation, and what that leaves us with is a singular H plus molecule on the reactant side and 0 on the product side. Okay, and we basically do the same exact thing with water, right? So there's 5 waters on the reactant side, 8 on the product side. So we're going to subtract 5 waters from each side, and we have 0 waters on the reactant side now, and only 3 on the product side. Okay, right here at the end of this page is your balanced redox reaction in acid. Okay, but they did ask for this one in base, and so all we have to do is 2 more steps. Okay, and so what I just showed you at the bottom of the page is the same equation right here. And all we do is neutralize our H plus with hydroxide or OH minus. And by neutralize, what we mean is this H plus molecule is going to combine with that OH molecule and create a singular molecule of water, right? So that's how we see 1 molecule of water appear on the reactant side below. Now notice, however, that I added 1 molecule of hydroxide to each side. That's because right before it, the equation above is completely balanced with every element in every charge. And so when we add something to one side, we want to do it to the other side as well so that our equation remains balanced. Okay? And so note here, we added 1 molecule of hydroxide to each side because we had 1 H plus molecule. If we had 5 H plus molecules, we would add 5 hydroxides to each side. Just kind of a side note there. Okay, and so once we add that OH minus, again, that reacts with the H plus to make water. Okay, we have the rest of the equation, and we have, again, our OH minus here. But when you create water through this method, you typically see water appear on both sides. And so your last step is just to subtract 1 molecule of water from each side, and now you get your full balanced reaction in base at the bottom, where your coefficient for water is 2 on the product side. Sorry, the wrong thing. Okay. Are there any questions on that problem? Okay. If there aren't, It is the, oh, I'm sorry. I forgot to have people, if you could just sign in the chat right now, and I'll kind of go through the, I meant to do that when we stopped to ask questions on that slide, and it kind of just escaped my mind. Okay, so this is a redox question that I want you guys to use for the first 4 problems. So this is kind of trying to take the multiple choice format, how you would see this. Again, your exam Friday is long answer, not multiple choice, but just to keep it in mind, it's also good practice. And so here's a redox. So the first 2 questions are just kind of regarding it. Okay, and so number 1 is kind of a labeling, what is your oxidizing agent? Number 2 is very similar to a multiple choice you got from last Wednesday's challenge problems, but this one we're kind of applying it to an actual problem that you were given, right? They're saying based on the equation, in the equation, what is your change in electrons? Okay. Number 3 and 4 are basically saying balance your equation, and then based on your balance equation, because it's a multiple choice question, answer. So basically they want you to balance it completely, and then you say what's the coefficient of water and what's the coefficient of hydroxide. So not just how many are there, but what side is it on is also important. Okay, because if you balanced it wrong, it might appear on the other side of the equation potentially. Okay, so if you need it, I'm just going to switch in about 3 seconds. Just a quick picture if you need it. Again, if not, it will be posted tonight. Okay. Number 5, again, just a very classic, what is the reducing agent for this reaction? Okay, again, I think all these multiple choice kind of represent how redoxes have been asked as multiple choice before. Now, number 6 is, I'll go to in just 5 seconds if you need, again, a picture of it, but number 6 is probably more likely what you'll see on your exam, because I know this has appeared in this format, I think at least 2 or 3 years in a row. I can't remember if this is how it came up last year, but for I think 2 or 3 years, this is the format they use. So I'll kind of just talk through it. So this is a classic redox long answer question. And so they kind of just want you to do little fill-ins based on the work. And they will look at it. So if you balance it wrong, you get all the questions wrong. They would go back. If you balanced it partially correct, they would give you some credit. How the rubric works exactly, I'm not sure. But basically what they do is at the top, they say, here's 1/2 reaction, balance it in base, okay? And so if you're gonna balance a half reaction in base, again, pretend you're balancing it in acid, and then once you've completely balanced that half reaction in acid, just convert that half reaction to base, okay? And so once you do that, they ask you, what is the coefficient of water? So that's kind of just a fill-in. And then they say, okay, once you've balanced that half reaction, it combines, this is the other half reaction, right? They combine to make the full redox problem, and based on the full redox problem, answer the other questions. So what's, again, a coefficient, how many electrons are transferred, what is the change in oxidation number, and again, kind of a labeling, what is the reducing agent. Okay, so again, number 6 is a very classic way to ask a redox question on a long answer exams. They don't typically just have you balance it and just go from there. It's typically sub-questions. So hydroxide is added to whatever side H plus appears on, because you can't have H plus in your final equation if it's in base. And so, yeah, it just depends. And that's all I have. So are there any other questions?
I just have like one little request that you could do if it's not too much of a problem. When you upload the videos, could you also like in the title or something put what chapter or what part of the chapter the video goes over, just so it's easier when we're studying for exams to go right to the ones on that chapter?
I can see if I can make a comment under it or put
Okay, thank you.
a little just, yeah. to convert to H2O. So I'm not quite sure your question, Daniel. Sorry. So you don't really convert it to H2O. You add hydroxide so that it reacts with H plus ions. And when they react, they become water. And then sometimes you have to subtract it if water appears on both sides of the equation. But I think that might address your question. Okay. If you want me to go back in, I'm just going to stop the recording here. But if anybody has any more questions, I'm happy to answer